Let's see what we got here. DSP operations, my favorite. I'm still learning how this stuff works.
It's magic.
It's magic, yes. So we'll talk about filtering and some of the other operations, software-defined radios, and DSP modulation and demodulation. So a lot of the newer software-defined radios actually do the modulation and demodulation digitally without using analog mixer circuits and modulator circuits. Is all done in the digital domain. What they're calling entirely software. It's really a mix of firmware and software. The software can change parameters, but the actual operations are done in the signal processing chips, which is kind of firmware. It's programmed. One of the SDR types that's pretty familiar uses what they call direct digital conversion, where they take the input signal from the antenna. It might go through an attenuator or preamplifier directly into an analog to digital converter. There's no front-end mixer, no local oscillator. And we call that direct digital conversion.
Get it to a digital signal.
It gets it directly into the digital domain, and then you do everything you need until you convert it back to audio. Yeah. So the end of this, you've got an analog to digital converter converting the RF, and the output of it is a digital analog converter outputting audio.
Consumer amateur gear, are they doing direct conversion above VHF, or is VHF just about the limit for amateur radio now?
My 9700, I think, is direct conversion.
On UHF?
I believe, I'm not sure. They might have a, for 70 centimeters and 23, they might down convert first. I'm not sure. But I'm pretty sure on 2 meters it's direct.
Yeah, two meters. I mean, they were doing one where they got some UHF, yeah.
And this also works in reverse when we're transmitting. Okay, we're taking the audio in, and
is that why years ago you would get an HF rig, and now the HF rigs have 6 meters, which is VHF? It's probably because of digital processing that they can easily accept that band also, isn't it? Because before
it made it easier. I don't know if that's...
It would have taken a lot of doing to get that additional band in that complete different frequency range. You'd have to have so many different...
Because I know that a lot of the little QRP radios that do multi-band go up to 10, but I'm not sure I've seen any that also do 6. Have you?
Well, you have the 818, 817, and then the 705. The KX3, you add a module for 2 meters, I believe. But all those other ones I mentioned, they do VHF and UHF.
Oh, okay. I guess the kind I build don't.
Yeah, but they are revered radios. I worship them. Even though they aren't digital.
Okay.
They're still great radios.
This is a kind of a block diagram of a direct digital conversion. This happens to be an ICOM 7300. So they're bringing the RF signal straight into the analog to digital converter. Then they digitally create 2 mixers and do a phase shift to get the I and Q signals. So you get the intermediate frequency, which is I, and the same signal shifted 90 degrees in phase, which is the Q or quadrature. And then with those two, you can play games digitally and do all kinds of wonderful things.
remember back around 2010 or so, people were doing that with high-end video cards. Because it hadn't quite, made it into
Yeah.
radio gear yet. Huh.
Yeah, that's got to be one expensive FPGA there, since that's basically the radio with stuff around it. What is meant by direct digital conversion as applied to software-defined radios?
D.
Incoming RF is digitized.
Yeah. So,
Charlie,
Charlie.
did you say Charlie or Delta?
I said Delta.
You,
You were talking about I and Q. I think you were trying to.
well, they do I&Q analog, and they also do it digital. Turns out it's easier to do stuff I&Q in the digital world. All right, so analog digital converters depend on the sample rate, and they've got to the point where they're doing sample rates up into the many megahertz. Not sure what the current ones are, which allows you to do the direct digital conversion. And the main thing that you have to do when you're sampling a digital signal is you've got to sample it at least twice the highest frequency of the frequency component in the waveform. So most waveforms, unless it's an absolute pure sine wave, is going to be some combination of sine waves at different frequencies and amplitudes. So it needs to be at least twice. And if it's twice, what you'll get is the same frequency, but you won't necessarily get any of the artifacts or anything of the amplitude. You have to sample it at more than twice in order to get more of the information. This little chart shows, and it's kind of showing what we call aliasing, where you're sampling it at less than twice the frequency. So you can see here down at sampling it at 0.3 hertz, and I'm not sure what I guess it's a 1 hertz signal, but at those sample points, it's going to appear to be a much lower frequency signal than it actually is. And even at 0.75 and at 0.5, at 0.5, it looks like a really low frequency signal, where when you're sampling it at twice the frequency, you're going to get the correct frequency. You won't necessarily get the correct waveform. Because if there's any little humps and bumps and things on there, it's not going to see those. So what aspect of receiver analog to digital conversion determines the maximum received bandwidth of a direct digital conversion software-defined radio?
Applejack.
A.
So how frequently must an analog signal be sampled so that the signal can be accurately reproduced?
Billy.
This guy called Nyquist came up with this theorem.
Yeah, it's B. Yeah.
He's been dead for a while. He's still doing it.
That's right. All these guys that did this stuff are dead. We did that.
You have to have somebody pick up your cause.
Voltage resolution. You need two things with the A to D: the minimum detectable signal level is determined by the reference voltage and the sample width. The reference voltage is the reference going into the analog to digital converter that it's basically a comparator. So it's comparing the input signal to that reference voltage. So the highest voltage that the analog to digital converter can handle is a signal equal to the reference voltage. If it's higher than that, it still looks like the reference voltage.
It sounds ugly.
Well, yeah. I mean, the AD doesn't know. I mean, it's just cut off at say it was 1 volt. If it's 2 volts, it's still going to say it's a 1 volt signal. So that's a pretty good clipping, like 50%. So that reference will determine the maximum detectable voltage. The sample width, in other words, how many bits wide the converter is, will determine the resolution, or the smallest detectable voltage.
Which equates to dynamic range, if I remember correctly.
That's one thing they call it. So in this case, if we had A to D converter with the reference of 1 volt, and it's a 10-bit converter, okay, it means that we can represent, each bit represents approximately 1 millivolt. So the range would be 1 millivolt to 1 volt. So it's just a simple matter of whatever your reference voltage is, you divide that by the number of bits, 2 to the number of bits, basically. This is a typical A to D converter called a successive approximation. It's the most accurate, but it's slow because it has to go through and approximate. It starts off with whether or not the input signal is higher or lower than the maximum signal, or the lower, depending on which way it goes. And if it's higher, it increments and sets the bit. If it's lower, it puts a 0 in, and it sequentially goes through by basically dividing by 2. If you do it in that direction, or multiplying by 2, they could work up or down. And you take that equivalent signal, you're feeding it back in as the comparator. So when it comes out, it's accurate to within the least significant bit of the converter. So what sets the minimum detectable signal level for a direct sampling SCR receiver in the absence of atmospheric or thermal noise?
Billy?
B.
Because atmospheric and thermal noise affect it. What is the minimum number of bits required for an analog to digital converter to sample a signal with a range of 1 volt at a resolution of 1 millivolt?
D. 10 bits.
Modern software-defined radios convert an incoming signal into 2 data streams, I and Q. They're 90 degrees out of phase. Q is what they call the quadrature signal, which is where the Q came from. And I is this normally the intermediate frequency. And the 2 of them will basically show you the amplitude and phase difference of the signal. And digitally, and I guess even analog wise, some of the radios do I and Q in the analog world.
So you need that quadrature if you ever go to phase, to looking at the phase modulation. But you normally wouldn't need it, would you? It wouldn't be used like for sideband or anything like that.
I don't know.
I guess it's possible. There's a use for it.
One of the things I need to learn more about is how I and Q actually, what they actually do with them, which I don't
Well,
really understand yet.
that's what all the cell phone stuff is running on, quite sure.
Oh, yeah,
Yeah.
but the math turns out that you can extract information by using the I and Q signals easier than doing the standard filtering and mixing. This typical I and Q modulator and demodulator, and how it would be done analog or in the digital world, you do the same thing, only in the digital domain. So the most common DSP operation is in the digital world is a fast Fourier transform. And what they're actually, it's a method to factorize a discrete Fourier transform. So what you're trying to do, since the waveform is composed of a mixture of different frequencies and amplitudes, you're trying to extract the coefficients or the amplitude for each of those frequencies. And that's what you do when you do the Fourier transform, is it comes out with what the coefficient is for each one of the frequencies that's in the signal. And you use that later on in for filtering and stuff in order to create the kind of bandpass that you want. This is kind of, and this is on the test now. This is showing, in this case, there's 4 samples. And what those actual values were and all the steps that they go through, and finally the actual output or the coefficients turn out to be these, and then you use them later just for the fun of it. So this is, I believe, the waveform at the top.
What mode is this talking about? Is it,
Um,
is it?
I'm trying to remember what this one is. The bottom is the Fourier transform output for this sawtooth wave. So you see it's every harmonic. In this case, it shows you what the waveform looks like. This was actually on the original, it's animated, but it doesn't animate on here. And as you do the 4th harmonic, it starts looking like pretty much like a sawtooth wave. If you add the 5th and 6th and 7th, on up, you eventually get a perfect sawtooth wave. Whereas the square wave is going to be the odd harmonics. And you notice it's 4 times or 4/3 or 4/5. Those are the coefficients. And if you did the Fourier analysis, those are the kind of numbers you would get out for each one of those frequencies so that you could reproduce like the square wave. And I wish I could remember what this one was. It's somehow related, but anyway. So what function is performed by a fast Fourier transform?
Charlie.
Converting digital or time domain to frequency domain. And it's called a fast Fourier transform because it's some mathematical techniques that allow you to compute it much faster than the standard discrete Fourier. a digitized signal can be digitally filtered. So we call these, or in a DSP, and we have basically two types, a finite impulse response and an infinite impulse response. They throw the adaptive in there, and it really confused me why they're doing that, because either of those could be an adaptive filter. The adaptive filter just means that you're modifying the parameters of the filter.
To suit your needs.
Well, you have, and that's the part I'm confused about. With the adaptive filter, you've got your input signal, and then you've got kind of a reference signal, okay, that you're going to compare the input signal with. In other words, the desired output. So it's one of those where you know what you're looking for, and then you keep changing the parameters of the filter to minimize the difference between what's coming in and what you want it to be. It's still a little hazy.
So you can take a signal.
Because I'm not sure what your reference is.
You can take a digital signal, modify it with the digitally to represent a signal that you desire.
Right. And you're doing it by looking at the output and comparing it to that desired signal. And, you keep iterating that until you get the error down to whatever is the minimum.
So what it's doing is it's modifying the digital data from certain frequency ranges. It's like
Well, and it doesn't have to be digital. I mean, this is
squashing the highs and
right.
lifting the lows and doing whatever to get it to an.
This is black magic.
Yeah. But
You can make everybody sound real confused.
in the case of the other two, there's in the analog world, most analog filters turn out to be infinite impulse response. In the digital world, you can have a finite impulse response. And the basic difference is if you put a step function, let's say, or an impulse into a FIR filter, the output will settle to zero or steady state. If you do it on an infinite impulse, it may sit there and ring forever and never settle. And that's a behavior you can see with analog filters where you get ringing depending on the Q of them and number of stages and all that stuff. So finite impulse response filters are much more stable, and they have a linear phase because the delay is just what they call taps or delay steps in the filter, depending on how many steps it has. So it's a constant delay for any frequency through it, where infinite impulse response is variable and squirrely.
So you delay it to reduce the feedback or?
No, you delay it because what you do and let's see what the next one is. Well, that's the adaptive. Well, let's talk about this one and then because it comes up next. This is kind of showing a block diagram of the adaptive filter where you have some desired signal that you're comparing your input with, okay, and you keep adapting the filter algorithm, okay, in order to get that error signal back to zero. What I don't understand is what the desired signal looks like. How do you know what it's supposed to be?
Lonnie Anderson, Bear Boss.
Maybe it's the most intelligible audio signal has certain characteristics like so much booming, and
I guess.
so many high.
Maybe, maybe you have a reference baseband signal or something. I don't understand that part. Okay. For a finite impulse response, what you do for the simplest one, and I've implemented one of these, and it's called a windowing filter, is each one of those steps, the Z minus one, is what they call a tap or a delay, which allows you to look at past samples. So what you're going to do is you take, in this case, what do they got? Well, N samples. So you're going to, in the standard windowing filter, the B or the coefficient, which is the B terms, is going to be 1 over N. So all you're going to do is add up X number of samples and divide it by the number of samples. So you've averaged over N samples. And the more of those samples, and each one is what they call a tap in the digital filter world, because you've got to store that sample somewhere. Okay, so you're delaying it in time by that amount. And the more taps or steps that you have, the lower the frequency, and you're basically making it, like in this case, it's a low pass filter.
So it's eliminating the garbage over time.
Right. You're just averaging all the high frequency stuff out. Okay. And if you make it wide enough, you only get through the lowest frequency. And it can take a lot of steps. I had to do 31 and I put noise on a signal in order to filter it out, this random noise. But sometimes they're much more than that. But then that also gives you delay through the filter. But it's a constant delay. It's always going to be that amount. Like I said, they're stable. It's non-recursive. It's a linear filter. Let me go back to it. There's only the sum of the input samples. There's no feedback from the output in this case. They say it's harder to implement basically because it requires more taps and more steps. I don't necessarily see that as harder, but
So what we're doing, you taught us about all these filters, pi, and all of that. So what we're doing, doing all of that in software, right? That's what we're doing here.
right. In this case, it's implementing what would be, depending on the coefficients, it would be a low pass filter if that was just a straight average. Now, if you change the coefficients for each one, you can get different.
So can it be a high pass filter?
Could be a high pass filter if you do it right.
Can it be a
Band pass, yes,
band pass filter? Can it be a noise filter?
yes.
So it can be
Any of those things.
software wise defined to be.
If you can do the Fourier in
Yeah.
order to find out the right coefficients. For an infinite impulse response, it's unstable because it's recursive and it's nonlinear. And what you're going to do is take samples of the output and sum them together, and in some cases, add them together with a sum of input samples. So you can have a combination going.
So there's no delay in this one.
Oh, there's some delay, but it's variable. So what kind of digital signal processing audio filter is used to remove unwanted noise from a received SSB signal? And in this case, they only mean from the list below. Which of the following is an advantage of a finite impulse response filter versus an infinite impulse response digital filter? Didn't I say that the FER was harder to implement? I don't know why they say that, but
You said the delay was the same. So it's gotta be.
right. And we talked about taps, and all those are a way to store previous samples so that you can sum them together. I guess the tap came from, if you did this in the analog world, you would actually use delay lines and taps on the delay. Maybe you still can. We used to be able to get integrated circuit that was a delay line with taps on it, and each tap was, microsecond or whatever delay. I'm assuming that's where the term came from. So the more taps you use, the easier it is to create a filter with the kind of shape that you want. In other words, you can get steeper slopes and control the pass band of the filter. In this circuit over here, the one on the left is the standard FER filter. We have a infinite impulse response over here on the right, and you see it's combination of both feedback, sums of the output summed in with the input. So every time there's a new sample coming in, you're iterating this loop. Why that's easier to implement, I'm not sure. So what's the function of taps in a digital signal processing filter?
D.
Very good.
I don't remember these questions,
You don't. How long ago did you take the test?
like 2 years ago.
Well, then you should have.
I know, I just,
I'm learning the ones, I don't remember that.
I know, like,
And I took it last year.
I don't remember that. I was whatever, 10 years ago.
Which of the following would allow a digital signal processing filter to create a sharper filter response?
Baker.
More taps. Okay. Really SDR operations, sometimes you use this technique called decimation, where in order to help processing time, because it takes some fairly powerful processing chips when you're sampling at multi megahertz and you're getting all these, 12, 14-bit, maybe even 16-bit samples coming in. If you only care about a lower frequency than the maximum that you're sampling, because the A to D doesn't know, it's sampling at whatever its sample rate is. You can reduce the effective sample rate by eliminating samples, and they call that decimation. So you go in and maybe you throw every other one away, which we have it. So now it only takes half as much processing power in order to filter it. When you do that, okay, you're now possibly sampling at less than twice the frequency of the highest component. So you're going to see aliasing. So that requires, in order to do the decimation, the anti-aliasing filter to somehow filter out those alias signals, which are the high frequencies that you're not sampling fast enough, so it looks like a lower frequency. Don't ask me how an anti-aliasing filter works, but that's what they're for.
Did we use one at the southern border?
Yeah,
So to decimate, you have to anti-aliasing.
right. You may have to, depending on how much you decimate.
Remember, I'm French, I gotta keep it simple.
Okay. This just shows again the aliasing, where when you're not sampling it at least twice the rate, then you can see some apparent signal that's different than what it really is. I guess that's a little different than the aliasing you see on video, where you have like angled lines and you see the stair step, and they call that aliasing also. I don't know that that's the same effect. What is the function of decimation?
Throw out junk.
They,
Baker,
That's probable.
All right. Why is an anti-aliasing digital filter required in a digital decimator?
A, alpha,
Because you're not sampling fast enough, because you decimated.
All
You
right,
need to throw out those things that are gonna be represented
right.
lower
I just don't know how you do that.
digitally.
Yeah, that makes it easy, right? If you can write the equation, you can do it. Oh, I guess I skipped it. So it's to remove the high frequency components. Okay. We talked about the I and Q, and by using the I and Q in the digital domain, you can generate or demodulate signals. And the one we hadn't talked about is one of the other techniques, particularly with single sideband. You can generate single sideband in the digital domain using I and Q. There's another technique where it uses the Hilbert transform filter along with Fourier transform, and it will, I guess, as I understand it, would be sort of the equivalent of a balanced modulator, where you're only going to get the sidebands and you can easily filter one out. So what's a common method of generating a single sideband signal using digital signal processing? Delta. All right.
delta,
I and Q. What type of digital signal processing filter is used to generate a single sideband signal?
her, Charlie,
Hilbert. I tried to find out what a Hilbert transform does, and I got more confused.